Good morning, this is Dr. Turner for Integrated Math 3. Today we're talking about 1.5, which is problem solving with constraints. 1.5 is going to be a pretty big section. We might spend a couple days on it in class, depending on time and all that good stuff. But 1.5 gets a little bit confusing because it's not simply just as black and white as the other sections that we've been covering. 1.5 really is a lot of word problems of understanding the algebra behind these things, covering everything from area to volume, et cetera, et cetera, et cetera. So again, it's not as black and white. It is a little more abstract. And because of that, it's not something that can just quickly be taught in a short tutorial video. It's something that, like a lot of math subjects, is going to need practice and your understanding and patience for. So bear in mind with that. I'm going to give you a couple examples. This is not an inclusive video. Because again, you could have any sort of number of constraint problems, but just to give you an example, we're going to go through here real quick and see what a couple of these might look like. Okay, so in your textbook, the Integrated Math 3 textbook, this is a very common example where you have a piece of plywood and you're basically trying to make a box out of it. So they're going to give you a diagram, something that looks like this. Again, my drawing's not perfect, but they're going to ask you, find the volume of a box that's cut out of this piece of plywood. They're going to assign a variable to each of these like so. So for instance, let's say we're calling this unknown value x. And assuming these pieces are a square, we're going to call these x's as well. And then in these diagrams, it's going to give you a measurement for the width and the length. So the width is going to be this whole thing here. And they're going to give you a measurement for the length, which is this whole thing here. Okay. So let's say I gave you a problem that says, find the volume of the given design for a box built from a piece of plywood measuring 20 centimeters by 60 centimeters. So in this problem, I'm telling you that the width is 20 centimeters and that the length is 60 centimeters. And I want you to tell me the volume of the box that you can make out of this piece of wood. Well, looking at this, if I was to cut this piece of wood the most efficient way as possible, I'm going to cut 4 slants going horizontally because I need 4 sides for the box going around. And then I need 2 pieces for the side. So I'm assigning values to W and L here. I'm saying the width is 40 and the length is 60. Well, if the width is 4 x's, that means my x is 10. And then here, if I say that x is 10, then that means that this length here has to be 50. 60 minus 10. So from this piece of plywood, I'm creating a box that measures 10 by 10, 10 by 10 by 50. And you don't have to draw the diagram, just as an example here. I'll write out the rectangular prism. So you don't have to make a diagram like I'm doing here. If the visual helps you, then I recommend it, but it's not required. But remember that anytime you're doing any extra work or showing that your teacher, you have some idea of what the problem is asking you for, that's always good for partial credit. If you just put an answer down and it's wrong, then we really can't help you out. So looking at this problem, I have 10 and 10 and 50. Right, so that's what I'm making out of this piece of plywood. And again, assuming my drawing's correct. So to find the volume, we're using length times width times height. So 50 times 10 times 10, that gives me 5,000. And because we're talking about volume, it's cubic centimeters. So there's a couple questions like that on the test, ask you to figure out what the volume is. Again, this is the problem that a lot of people struggle with math, in that, I could create an infinite number of different types of constraint problems in this section involving different areas, different volumes, but there's no way to create every single example that's possible. It's just not how it works. So that frustrates a lot of students because they expect to just see an example that's given in the diagram and be able to solve for it. That's just not how it works. So, I'm giving you just a couple of ideas here, but obviously the lecture will cover it more in detail. Let me give you another example. So I have a tea candle made from let's say 100 cubic centimeters of wax. If the candle's radius is twice the height, what radius and height should it have to the nearest tenth? So as always, you'll be told how to round or specify your answer. So here I'm making this candle, which would be, again, here's my candle. It would be cylindrical in shape. I'm making it out of 100 cubic centimeters of wax, which is a lot, but that's fine. So I'm saying that the radius, or R, is twice the height. The radius is twice the height, then what I'm looking for is what radius and height should it have rounded to the nearest tenth. Okay, so let's write this in terms of an equation. I have a radius as 2h, it's twice the height. My volume formula for a cylinder is pi times radius squared times height. And I'm trying to solve for two variables, r and h. Well, I can't do that if this is the only thing that's given to me, because I need to rewrite this in terms of a single variable I'm solving for. So I'm going to use r equals 2h and plug in 2h for r here in the equation. So I plug in 2h, being careful that I have an exponent there. I get volume equals pi times 2h squared times h. I can also plug in the volume because I said I have 100 cubic centimeters. So 100 equals pi times, be careful, your power of a power rule. All right, if I'm doing 2h squared, that ends up being 4h squared. Work this out, 100 equals, and I'm going to rewrite it, I have 4 pi h cubed. That's your commutative property. You can rework those things, make sure all the integers or coefficients are all on the same side. So to solve for this, I'm going to divide both sides by 4 pi. And at this point, because it's telling me to round to the nearest tenths, that means I'm going to use a calculator to find that approximation. I'll divide both sides, or sorry, I'll take the cube root on both sides to get h by itself. So my answer is going to be the cube root of 100 divided by 4 pi. At this point, this is something you want to pull out a graphing calculator for, or a Desmos or a scientific calculator, something that has a pi key. So if I do 100 divided by 3.14, and then I'm taking the cube root, that is going to give me an approximate value of, so you plug it into the calculator, and then after you get that, you're going to get 1.9946. And as we're rounding to the nearest tenths place, that is going to be approximately, because we round it, 2.0, and we're looking at the height, so this is 2 centimeters. Again, we could cover an infinite number of answers that are going over these types of problems. We'll cover more in class, but this is just kind of an idea of what types of problems to expect on the assignment for 1.5. If you guys have any questions, please reach out to me. My email is mturner@psasb.us. And other than that, have a good day, guys, and I'll talk to you later. Bye.